plus epsilon times delta E by delta T. So we have now the expected symmetry between electric and magnetic fields, except for the fact that as there are no magnetic monopoles, the divergence equation cannot be symmetric. Now, the set of four Maxwell's equations, which were written in 1864, are thus: divergence of D is 4 pi rho, divergence of B is 0, where D is epsilon times E and B is mu times H. Curl of E is minus 1 upon C delta B by delta T, and curl of B is mu by C J plus delta D by delta T. The first and the most important consequence of this set of Maxwell's equations was the realization that the electromagnetic field propagates in space and time like a wave with a finite velocity. Interestingly, when Maxwell concluded this and got the wave equation, it was already known through Hertz's experiments that electromagnetic waves do exist. Hertz's experiments were known, and therefore this was a mathematical certainty now that we have. How do we get it? Now consider the equation curl B equal to mu upon C J plus delta E by delta T, and taking its curl, one gets curl of curl B is mu upon C into curl J plus epsilon times delta of curl E upon delta T. That is, you just use the fact curl E is delta B by delta T. Therefore, it gives minus mu by C curl J minus epsilon by C delta squared B by delta T squared. But now you again use simple vector identity. Curl of curl B is nothing but gradient of divergence of B minus del squared B. So, substituting this in the other equation, now along with Gauss's law of magnetostatics where divergence of B is 0, this takes the simple form minus del squared B is mu upon C curl J minus epsilon by C delta squared B by delta T squared, which in the case of absence of currents when J is 0 yields the wave equation del squared B minus epsilon mu by C squared delta squared B by delta T squared equal to 0. Taking the correct dimensions x upon C and T, one can see that the above equation says that the magnetic fields move as a wave of velocity root of epsilon mu, which is denoted as C. It is easy to see the electric field E also satisfies a similar equation. Delta squared E is minus epsilon mu by C squared, delta squared E by delta T squared equal to 0. Both are second order partial differential equations. This is a very clear illustration of the successful application of mathematics, depicting how the mathematical symmetry induced a new insight and an extension for physics. As one can see, the electromagnetic waves are characterized by sets of second order partial differential equations. In order to solve them, one will need help from complex functions. For example, a set of plane electromagnetic waves in one dimension are represented by solutions of the form E equal to E naught exponential I k dot x minus omega t. In fact, as we know, light is a form of electromagnetic wave whose propagation can be understood through the analysis of wave equation and associated solutions. This particular aspect, that light is electromagnetic wave, opened out a new vista in physics and gave motivation and also birth to new physics of the 20th century. One of the ways to understand this universality, that is same appearance to all observers of the physical world, is by ensuring the invariance of the laws of physics under transformations of space-time coordinates. If you remember, Galilean transformations had already the invariance property for Newtonian equations. Newtonian mechanics follows Galilean relativity. But unfortunately, we saw that, so this is the Galilean relativity, this you remember, x prime is x plus u x t plus c1, etc. These are the equations or transformation between x and x prime, and t was same if you remember in Galilean relativity. We had such that these equations saw to it that the Newtonian equations are invariant under these transformations. Unfortunately, Maxwell's equations of electrodynamics are not invariant under these transformations, and this was a well-recognized difficulty at the turn of the 19th century. This difficulty of incompatibility between classical mechanics and electrodynamics played an important role in the development of the theory of relativity by Albert Einstein. Einstein's realization of making time relative and having a four-dimensional space-time structure for doing physics helped solve the problem of incompatibility between mechanics and electrodynamics. How was that? Now, the geometrical requirement of having distance between 2 points invariant for all inertial observers automatically gave the set of required transformations the Lorentz transformations. I must mention here that historically, Lorentz already had searched for the set of transformations which can keep Maxwell's equations invariant under transformation. However, that was done mostly with the idea of only keeping the laws to be invariant. There was no other motivation. However, apart from keeping the invariance of physical laws for all four-dimensional inertial frames, Einstein asserted that the velocity of light for all observers to be the same as fundamental postulates. So what Einstein did at the turn of the 19th century toward 20th century was that you have space and time not as different but together, space-time framework. Then you claim that in this framework the inertial frames are built, and then you ask for the invariance of the physical laws, both mechanical and this one. That means that you need to look for the transformations, and for that he used only one concept. The velocity of light is same for all observers in all directions. Now, with this, the invariance of the metric function ds squared leads to, if ds squared in the frame x, if you call it as this bilinear form, eta mu nu dx mu dx nu. In the x prime form, let's call it eta alpha beta dx prime alpha dx prime beta. Between these two sets of coordinates, if I were to have a transformation, now dx prime alpha, because x and x prime are functions of each other, you get delta x prime alpha by delta x mu dx mu. Using this, one gets the equation eta mu nu dx nu is this, as given by 3.2. And now, which essentially gives the transformation law for this one. Because what really happens is, when you take this into picture, and then you have for the same, this alpha beta are dummy indices here, and now you can change cyclically mu nu. You take, say for example, with x xi, one more coordinate, you can write three equations, and then making some algebraic trick, you can get that this relation is given by this. This means that this Minkowski metric eta mu nu, or also called the flat space metric, transforms in this form. Now, differentiating both sides with respect to x xi, now one finds that eta alpha beta, this is 0 on this side because it is constant. You have this, and two other equations similarly, 3.5 and 3.6. Just take to add two of them and subtract the other, and that gives you straight away relation twice of eta alpha beta delta squared x prime alpha by delta x nu into delta x prime beta by delta x xi equal to 0. Now, this term, as you notice, is the Jacobian of the transformation between the frames x and x prime, which cannot be 0. Therefore, you have to conclude that delta squared x prime mu by delta squared x prime alpha by delta x nu squared should be 0, which shows that if you want to look at a transformation which is such that the metric is kept invariant, then it has to be a linear transformation. Now, what is a linear transformation? Now, here example, the most general linear transformation is given by x prime alpha is lambda alpha mu x mu plus a mu, where lambda alpha mu represents an orthogonal 4x4 matrix having constant elements and a alpha are any 4 constants. Now, we shall now consider two primes again, O and O prime, as we did earlier. The transformation from x to x prime, we say that this is moving with respect to only in one direction, then the change will be only in that direction. Let us take some arbitrary functions like this and substitute this in the earlier equation. ds squared, because this has to be the same. dt prime squared c squared minus dx prime squared should be c squared dt squared minus dx squared. So I substitute here, and immediately you find that matching the terms of equal dimensions, you get a1 squared minus c squared a2 squared equal to 1, and this one and this one. 3 equations. But you need fourth equation because there are 4 unknowns. Now consider a point P in O prime whose coordinates in O are x and t. As O prime is moving with respect to velocity v, and the point P is at rest in O prime, you get dx prime is 0, but dx by dt is v. Therefore, you get a fourth equation, a1 v plus b1 equal to 0. Now, having gotten 4 equations and 4 unknowns, you can simply solve them, linear equations, and you get the unknowns a1, b1, a2 and b2. So, assuming that at t equal to 0, you remember that there are still plus or minus signs are there. You need to identify which is the correct sign. For that, assume that at t equal to 0, the two frames were coincident, and for t greater than 0, O prime moves away from O in the positive x direction. One can fix the correct signs and finally obtain the transformation to be x prime is x minus bt by root of 1 minus v squared by c squared. Y prime and z prime do not change. T prime is t minus vx upon c squared by root of 1 minus v squared by c squared. These are indeed a well-known special Lorentz transformation. In fact, one can indeed generalize these transformations by considering the motion of the frames not necessarily along any one particular direction and get the general Lorentz transformations. They are interesting and important to note that these sets of transformations form a group called the Lorentz group. The representations of the Lorentz group played extremely important role in the development of modern physics in the 20th century, particularly in the context of atomic, nuclear and particle physics. Perhaps many of you know that vectors and scalars belong to the family of tensors, with a vector being a tensor of rank 1, a scalar of rank 0. In general, tensors of higher rank are extremely useful objects due to the fact that they are by definition covariant objects. Tensors of rank 2 are often encountered in the study of fluid mechanics and elasticity, particularly as stress tensor. The most important application of tensors appears as elements of differential geometry, particularly Riemannian geometry, in the development of Einstein's general theory of relativity, which indeed is the most beautiful and perfect theory of gravitation, the fundamental force of nature. By definition, general theory of relativity is the extension of special theory of relativity to include the applicability of all physical laws to all observers, irrespective of their states of motion, including the accelerated ones, and thus bring the gravitational field into the space-time arena. In other words, one wants to write physical laws in covariant language, and thus the requirement of tensors. It is the mathematician Marcel Grossmann who introduced Einstein to the language of tensors in Riemannian geometry, which is the basic background for general relativity. Now, curved geometry Euclidean geometry depends on parallel postulate, and now the mathematicians Lobachevsky wanted to deviate from parallel postulate by saying that there can be more than one parallel line, and he got the hyperbolic geometry. But Riemann said that no parallel line can be drawn through the point outside the point given. Spherical geometry was obtained. This is surface with a positive curvature. Now this is the geometry which in fact is the extension of Gaussian geometry, which showed that Einstein the lead to do his general relativity, to frame his general relativity. The distance function in special relativity was put in a tensorial form in this way. In general relativity, the theta j's were constants. Now we have a general one where gij's are functions and they represent potentials. And now we can connection three index components which represent the acceleration of a particle following a geodesic, and the Riemann curvature tensor which represents the relative acceleration between particles. With these, the equations for the gravitational field can be obtained similar to what in Newton's theory we did for Poisson equation and Laplace equation, which is again essentially a second derivative of the potential proportional to the matter density. So here we need 10 equations because there are 10 unknowns. And so Einstein wrote it in this form, where Rij and R are contracted curvature tensors. With this, now Einstein looked for something, and luckily again two mathematicians, Relativity and Bianchi, they had discovered a beautiful identity called Bianchi Identity, which was satisfied by this. Lo and behold, if you now use this one, it would give you the conservation law, Tij semicolon j equal to 0. Therefore, Einstein gave the constants a and b these values, and thus wrote his famous equation, Rij minus half Rgij is equal to kappa Tij, where this represents the geometry and this represents physics. In fact, this identification was made similar to Poisson equation.